Welcome back. So we're discussing this circuit, the basic SR latch, and last video we actually set up a reset state by putting S is equal to 0 and R is equal to 1. And then later on we maintained this state by putting S is equal to 0, R is equal to 0. Right? Now let's consider the same circuit. We are still analyzing it. So quickly I will draw it. This is the upper NOR gate. This is the lower one. Then we have feedback connections like this, a direct connection, then a direct connection, and another feedback connection. Fine. And this is S, this is R. This as usual is Q bar, this is Q. I'll make a copy of it. Okay, so now let's put up the third scenario wherein now I will put S is equivalent to 1 and R is equivalent to 0. So something like this. S is equivalent to 1, R is equivalent to 0. Now the upper NOR gate has one of the inputs as 1. And again, the behavior of the NOR gate is if one of the inputs is 1, output will be 0. So this input, it will trigger this output, and this output will go to 0. Then because of the feedback connection, it will be fed back here. So this output will go to 0. The lower NOR gate has both the inputs as 0. So this will trigger this output. It will go to 1. And then later on, this will be fed back, which makes the other input of the upper NOR gate also equal to 1. So the sequence of events is something like this. S is equal to 1 and R is equal to 0. First of all, Q bar will be triggered to 0. Then Q will be triggered to 1. Fine. And immediately after this, if I now again put S is equal to 0 and R is equal to 0, I mean, we have attained this in the previous state. R is still 0. This is 0. This is 1. Now I am changing this also to 0. But the second input of the upper NOR gate is still equivalent to 1 here. So this means Q bar will still be 0. This will be fed back here. It will still be 0. Q will be 1. So this means even if I change S is equivalent to 0, Q bar will still be 0 and Q will be 1. Fine. So I can say that by putting S is equivalent to 1 and R is equivalent to 0, we are triggering, initiating, whatever you want to call it, a set state wherein like I said, we are basically interested in this output. This is just for explanation purpose. A real latch or a flip-flop only has one output, right? One practical output, and that defines the state of that circuit, right? So the set state means it will be storing 1. So this will actually initiate this state, trigger this state, and then later on by putting immediately after this by putting S is equivalent to 0 and R is equivalent to 0, the set state is maintained. So I am maintaining the set state. Fine. And this defines the behavior of this circuit. Now, the basic requirement for storing a bit was I should have a circuit, I should have a block that stores both 0 and 1, and both 0 and 1 should be retrievable when we like it. And we have actually achieved this I mean, this behavior using this simple basic SR latch. I'm able to store 0 by putting S is equal to 0 and R is equal to 1. Then I'm able to maintain that state. Yeah, store that 0 indefinitely by putting S is equal to 0 and R is equal to 0. Then later on, I'm able to store 1 by putting S is equal to 1 and R is equal to 0. And I'm able to maintain that state indefinitely by putting S is equal to 0 and R is equal to 0. Fine. So we normally show this behavior in terms of a state table. It is just like a truth table, and I will draw it here for this particular circuit. So I have S and R. I have Q, which defines the state of my circuit, and as a complementary output, I also have Q bar. So I started with this. Let's draw a small table here. S, R, Q, and Q bar. So we started with the condition where S is equal to 0 and R is equal to 1, which means a reset state, and this was the output condition. So this was my reset state. Yeah, fine. Then immediately I changed my inputs to 0, 0, which actually maintained this state. So I can say this was triggering of the reset state. This was maintaining the reset state. Fine. Then later on, I changed S is equal to 1, R is equal to 0, which made Q is equal to 1, Q bar is equal to 0. This was the set state, the triggering of the set state. Then I changed back to 0, 0, which maintained this state. So this maintained the set state. Fine. And sequential circuits may we normally show it using a timing diagram. Right? So if I quickly draw a timing diagram here based on this truth table, this state table rather, and it will be okay, it's already here. So we started with S is equal to 0. So this is S being 0 for first interval, then S being 0 for second interval, then it changes for 1, comes back to 0. Fine. And for R, let's choose another color. R was 1 for the first interval, then dropped to 0, second interval, continued 0, third interval, and again 0. Okay, so for your reference, I will draw the intervals. So this is my first, should use a different one. This is the first interval, the second one, third. Fine. So this is S 0, 0, 1, 0. And then this is reset 1, 0, 0, 0. And then if we plot Q, there will always be gate delays associated with it, but if we plot Q, it will be zero here, then 0, then it will go to 1, 1. Fine. Like I said, we are mainly interested in Q. This actually tells the state of the circuit. So for the first two time intervals, of course, there are some gate delays. I'm not taking that into consideration. I'm assuming an ideal behavior, but you can always adjust those delays. So this is my reset state. Isma, the first time interval. This is setting up the state. This is maintaining. So this is setup. This is maintain. Fine. Then this is the set state. Again, I can subdivide it into two small portions. This is the setup, and this is maintain. So this is the basic unit of memory that I can have. If we actually use a block to represent this, we show the two inputs as S, R, and normally we are interested in one output Q, but for the sake of, I mean, explanation, we also show Q bar. Fine. So this is S, this, yeah, we normally show it internally, S, R, Q bar, and Q. This is the basic SR latch. Now, if you are keen enough, you must have observed from this that one of the input combinations is missing. We have 0, 0, we have 0, 1, we have 1, 0, but we don't have 1, 1. Fine. So we'll consider that condition separately because that is basically the problem with this circuit. It kind of gives an indefinite state. So that we'll be discussing in the next video.